Hello, here's a question on circular motion. We've got an item of clothing placed inside a washing machine. Drum of the washing machine has radius of 30 centimeters. So radius 0.3 meters. Rotates about a fixed horizontal axis. Constant angular speed of 900 revolutions per minute. So let's flip that over to a frequency because we either want frequency or period on this. I mean, they're more or less the same. So frequency, the number of revolutions per second, we divide by 60, so we've got 15 hertz there. So of course the period of oscillation would be 1 over 15. That's the amount of time it takes to do one revolution, 1 over 15 seconds. That is also going to give us our omega off of this, because you remember that omega, our angular velocity, is 2 pi f. So we've got an omega of 30 pi radians per second. So that's good. Let's put, well, that's radians per second. Let's put it down here, might as well. Radians per second. Model the item of clothing as a particle of mass 0.8 kilograms. So m equals 0.8 kilograms. Assume the clothing travels in a vertical circle at constant angular speed. Fine. Find the minimum magnitude of the normal reaction force exerted by the drum on the clothing, and find the maximum magnitude of the normal reaction force exerted by the drum on the clothing. Right, so let's think about what's actually happening inside this drum then. So as the washing machine's going round, it's meant to be a circle, but it's close enough, not bad for me. Let's think about what's happening at extreme points here in terms of the motion. So let's put the clothing, if say it was at the top, it was at the bottom, and it was at either of the sides. I mean, the sides are going to be identical to each other, but these are sort of our extreme points, aren't they? Now we've got to remember here that it's circular motion. We need to have a centripetal force which is acting towards the center of the circle, towards the center of the drum. And that needs to have, because we're moving here at a constant angular speed, that's what it's told us in the question, we need to have this constant acceleration and this constant centripetal acceleration of omega squared r. And that's got to come from our centripetal force. So how is this centripetal force changing? Now, when we're at the top, we've got the weight of the object acting towards the center of the circle, the weight of the clothing acting towards the center of the circle, plus we've got the reaction force. So that's fine. When we're at the bottom, we've got now the weight acting away from the center of the circle and the reaction force going towards the middle. And when we're at the sides, we've got the reaction force going towards the center and the weight still acting down. So you can see here, this is why the reaction force is changing. When we're at the top of the circle, the weight of the clothing is adding to the centripetal force. So we need less reaction force. When we're at the sides, the weight doesn't contribute at all to the centripetal force. And when we're at the bottom, it's actively acting against it. So we're going to have a higher reaction force when we're at the bottom. So we've got our minimum reaction force at the top, and we've got our maximum reaction force when we're at the bottom. So let's put all of this in. We're doing F equals ma here, because we know what our acceleration has to be. That's got to be omega squared r. So, okay, so when we're at the top, we've got that mg plus r min is going to be equal to mr omega squared. And then when we're at the bottom, we're going to have r max minus mg is equal to mr omega squared. So you can see these things are pretty similar to each other here. And now all we've got to do is plug in our numbers. They're just changing. One of them we're going to be adding mg, and the other one we're going to be taking it off. So for r min, we've got m, which is 0.8, times r, which is 0.3, times omega squared, so that's 900 pi squared, and then we need to take off mg, which is 0.8 g. So let's get rid of a lot of these zeros here. So that 0, that one, and that one all cancel with each other. So we've got 3 times 8 is 24, multiplied by 9 is going to give us 216. So we've got 216 pi squared minus 0.8 g. That's what we've got for R min. If I just tap that into a calculator, that's coming out at around about 2120 newtons. And then our max is just going to be, well, we've still got exactly the same 216 pi squared because that's our MR omega squared, but this time we're adding on 0.8 g, which isn't going to be much different because 0.8 g is not a lot. So by the time we've added that on, we're getting around to 140, give or take, rounding it. I mean, I've rounded these quite a lot. I mean, you can see there's not, I mean, 0.8 g is not 10. So we're not having a 20 difference between these. You know, you're looking at more like 8, aren't you, for the difference in these? But looking at the accuracy of what they've given us here in the question, I mean, this 900 revolutions per minute, 0.8, 30 centimeters. I mean, they're not high accuracy figures here. So go into this, if I was going to give an answer here to 4 significant figures by breaking this out of 2120, 2140, well, we just don't have the accuracy for that. So I'm keeping it there at that 3 sig fig. So yeah, quite a straightforward sort of fairly standard opening question for circular motion. They love these washing machine ones. But it does highlight this thing again that sometimes people get confused with when they start on circular motion. You know, this idea of the centripetal force. The centripetal force is just the things that are acting towards, the forces that are acting towards the center of the circle that the object's moving through. So it's made up of a number of forces potentially. I mean, you can see this just from what we've drawn out here on the diagram, that when we're at the top, the centripetal force is the combination of the reaction force and the weight. When we're at the side, is just the reaction force. When we're at the bottom, is a greater reaction force because we have to then counteract the weight of the clothing. So it's not an extra force. It's not something new. There's not, oh yeah, well, here's a thing that is the centripetal force. It's a category of force. It's the resultant force that is acting towards the center of the circle that the object is moving through. So yeah, it's that category. And then aside from that, we are just, again, doing Newton's second law. We're coming in doing F equals ma, but we've got nice formulae available to us for saying what the acceleration is. Okay, in this case, I've done omega squared r. Of course, remember our other option is the v squared over r. That's our other way of doing the centripetal acceleration and quantifying things there. But yeah, it's a nice starter question, this one. Actually, just to add on this before I forget at the end, in case any of you are wondering how then the washing machine actually works, of course, this is why we've got the little holes in the drum of the washing machine. So they're holes that the clothes can't go through because they're small. So you're still getting the reaction force from the drum on the clothes, which is keeping the clothes moving around in a circle. But when the water goes over the hole, then you're going to have drops of water which don't have the reaction force. So if that drop of water doesn't have a reaction force from the drum, it can't move in a circle, and it's going to move through the hole and out of the inside of the drum. So that's how we're getting rid of water by spinning it around. That's why we've got those little holes. So yeah, the clothing gets a reaction force and the water doesn't, or at least some of the water doesn't. So it's a good way of removing the water just by spinning it around in something that's got holes. It's like salad spinners and everything else, isn't it? It's all the same thing. They've all got the same setup, that you want to give something a centripetal force, but the water don't give it the centripetal force. and eventually you're going to be getting rid of enough of the water to dry it out, or at least dry it out significantly.